We're going to go ahead and get started. Before I welcome our guests, I'd just like to invite those who have not already done so to please subscribe to our YouTube channel, Magnimind Academy, where we upload recorded sessions of these talks so you can watch them later. You can also comment any questions on YouTube or just let us know about what you think about today's talk in the comment section below. Now I'd like to welcome Pavel Dmitriev, who will be presenting his talk on incorporating AI in A&B testing. At Magnimind, we really try to find speakers who are really well qualified, just as him, who can deliver workshops like these filled with current information and a new perspective that goes along with our data science education programs. These programs range from focusing on the fundamental skills of data science all the way to helping a career change into the industry. And our goal at Magnimind is impacting as many careers as we can, and really this is just one way that we do so. Dmitriev joins us from Outreach, a company focused on utilizing machine learning to optimize sales and customer interaction. There, he is the VP of Data Science and has a list of duties long enough for a short essay. Before this role, Dmitriev's career includes a stint with Microsoft, Yahoo, and his own side project that is a website which helps to relieve stress during the holidays called destress.us. If somehow you're still unsure whether Pavel is qualified, I'd like to add that he got his BS in Applied Mathematics and System Programming from Moscow State University and then got a PhD in Computer Science from Cornell. We at Magnimind are extremely excited to host him. We'd like to ask you now to please give your full attention to Pavel Dmitriev.
All right, thanks, Thomas. Now I'm worried. Am I qualified? I'm not qualified. But A/B testing happens to be one of my favorite topics. I've spent probably about a decade working on it, on various aspects of A/B testing. And what I'm going to talk about today is how we can use A/B testing to help make our AI solutions better. Rather than, as the title I think may suggest, rather than how to make A/B testing better using AI. And we could talk about that in the Q&A session. I have some thoughts on it too, but this talk is about how to apply A/B testing through AI. And I'd like to start with this quote from Jeff Bezos, because I think it really motivates the goal of this talk very well. That the most important single thing is to focus obsessively on the customer. Our goal is to be Earth's most customer-centric company. And I think, as you all know, they are doing pretty well by focusing on that goal. So what I want to ask, the question I want to ask in this talk is, how can AI and machine learning developers become more customer focused? Are we really customer focused? Are the methods that we use to develop AI and machine learning solutions really customer focused? And how can we become more customer focused? So this is an outline of my talk. I think many people here probably are familiar with A/B testing, but I'm still going to give you a quick introduction and a few fun stories, as well as a few examples of real experiments. Then I'd like to talk a little bit about why A/B test AI systems. Because in AI and machine learning, we've got a very well-developed methodologies for evaluation and for making sure our models are actually performing well. So what does A/B testing add to that? And finally, I'm going to share 5 of my favorite pitfalls and lessons from actually applying A/B testing through AI, which is something that if you are going to actually try to do it, hopefully will be helpful for you. All right, so let me start with a story. And this is actually a true story that happened in Bing in the beginning of 2012. An engineer in Bing had an idea. And the idea was very simple. He wanted to take the first sentence from the description of the ad and just move it into the title. So that's all. It's actually just a few lines of JavaScript to implement it. So this was his idea. But it was one of the hundreds of ideas on the table, and compared to others, this one seemed like, man, nothing special. So as it usually happens, it was put in the backlog, and it stayed there for 1 month, and another month, another month, another month, and 1 more month. And after about 6 months, it became clear to this engineer that this idea is never going to rise to the top. It's never going to happen, right? But then he thought, well, this is actually trivial to implement, just a couple of hours of work. So he just did it in his free time, and then he started an A/B test, which I'll talk about, I'll describe later, which is a standard way of how all the new features in Bing are evaluated before they are shipped to production. And immediately after he started an A/B test, an alert fired. And the alert said that revenue is abnormally high. Something is wrong. We are making too much money. And normally when something like this happens, it actually indicates a bug. However, in this case, there was no bug. This simple idea increased Bing's revenue by 12%, which is over $100 million per year at that time, without actually hurting any of the user experience metrics. So what is the lesson from this story? The lesson is that we, as humans, are pretty bad at assessing the value of ideas. Now, this was probably the best revenue-generating idea in the whole history of Bing, but it was badly rated and delayed for months. In fact, those 6 months of delay cost Bing $50 million. And also, the reverse is true as well. It's not only that we cannot recognize good ideas, we actually sometimes can propose pretty bad ideas as well. We ran a study again at Bing, and we found that out of the ideas that did get prioritized and developed, actually only a third of them were good for users and for business. And the other third was neutral, and a third was bad. So it's a very humbling statistic if you think about it. Like, you can imagine yourself being a product manager and you have an idea, you believe it's good for the users. In fact, in reality, you are as likely to be wrong about it, and your idea is as likely to hurt users as it is to help them. And this kind of statistics were reported by many other companies, Netflix, Amazon, Google, all over the place. It's confirmed that really we cannot assess the value of our ideas very well. And it's not only happening in software engineering. For example, in sales, where I currently work, best practices are abundant and contradictory. For example, if you search online about what is the best day of week to contact a cold prospect in order to have higher likelihood of converting them, there is advice for every single day of weeks and some justifications why that is the case. And in medicine, where it's particularly important to evaluate ideas correctly, new drugs, where it's not just a matter of making more or less money, but potentially a matter of life and death, there they do not trust the experts. FDA, EMA, they mandate the use of randomized controlled trials, which is essentially A/B tests. So the takeaway from all of this is that we cannot trust our gut. If we want to make the right choices, we need data from real users. And the best kind of concise way to express it that I found is this quote from Admiral Grace Hopper, the first woman admiral of the United States. Just one accurate measurement is worth 1,000 expert opinions. All right, so with that, we hopefully settled on the fact that we need to use data to evaluate our ideas. However, it is also very important to know how exactly to use the data. And I think everyone is familiar with this phrase, correlation is not causation, but I am very much surprised by how many people, even those who know this, still use correlational data in a causal way. And the argument usually goes like this, that the only data I have is the correlational data, and using some data is better than not using any data. So I'm going to use correlational data and assume that it's causal and make my decision based on it. So this is a very dangerous way of thinking, and let me just show you this fictional example of what can happen if you do that. So I live in Seattle currently, and you may have heard that Seattle is known for its rain. In fact, just rain today in the morning. And I personally do not like rain. And I notice, suppose I sit in my home currently, and I noticed a very interesting thing, that whenever I see people on the street carrying umbrellas, then very soon it starts raining. So it's an interesting correlation. Now, I may conclude, interpret it in a causal way, and conclude that it is the umbrellas that probably causing the rain. And then I have an idea that if I ban the umbrellas, the rain is going to stop. And I'm going to be happy, the sun will be shining. But of course, this makes no sense at all. Banning umbrellas is not going to stop the rain. However, it actually is going to make everyone a lot more wet. Right, so the point here is that relying on correlations isn't just going to be neutral. Very often, it may be harmful. All right, so how do we then use the data correctly? And there are many methodologies and approaches that exist, but the best scientific kind of gold standard for using data to evaluate ideas is A/B testing. So what is A/B testing? Here is a quick example of a simple A/B test. Suppose we have users who are coming to use our product, for example, our website. So what we are going to do is we are going to randomly assign each user as they come in for the first time into one of the two variants, either into the control variant, which is going to be the normal version of our product, or into the treatment variant, which is going to be a version of a slightly modified version of our product with that new feature X. And this new feature X is that idea that we are trying to evaluate. And we want to know, is this new feature X good or not? Does it help users or does it hurt users? So we allow this experiment to run, users to continue to use these two variants of the product for some time. And during that time, we collect data on their usage. And then at the end of the experiment, we compute metrics based on the data for these two groups, treatment and control, compare them, and determine the winner. Now, what's nice about this setup is that if at the end of the experiment, we actually see difference in metrics, it really can only be due to two reasons. Assuming the whole thing got executed correctly, there could only be two explanations of why the same metric, for example, conversion rate, is different between these two groups. The first explanation is that that difference is due to our new feature X, because that's the only thing that's different between control and treatment, this new feature X. So that's one explanation. And the second explanation is that perhaps it's just a random noise. Now, just somehow by chance, we happen to put more higher converting users into control group versus treatment, or vice versa. So to get rid of the random chance hypothesis, we do statistical testing. And then if at the end of the experiment, we see a statistically significant difference in our metrics of interest, then we can be reasonably sure that that difference was actually caused by our new feature X. So this is a basic A/B test. And you can also hear other names in the literature: controlled experiments, randomized clinical trials. All of them mean essentially the same thing. Now, there are also other versions of A/B tests, for example, ABC tests, where you have two different treatments. And as I already mentioned, at the end of the experiment, we must run statistical tests. We cannot just compare the numbers in order to eliminate that chance hypothesis. And again, why we like A/B tests is because it is the best scientific way to prove causality, which is what we want. We want to know that our idea, our new feature actually caused changes in those metrics that we are interested in. All right, so this was a quick introduction to A/B testing. Now let's look at a few examples. And the way we are going to do it is we are going to do it as a game. And here I'm going to trust you that you're going to play fairly. In the normal situation, when we do it in person, it's very obvious. But right now, each one of you can do whatever you want. But I trust you're going to play fairly. So what we are going to do is I'll show you 3 experiments. And each one of them had enough users for statistical validity. For each experiment, I'll tell you what is the success metrics. And your job is going to be to guess the result. So the way we can do it, you can stand up. And the way you're going to choose, well, I guess you don't actually, I would say even at home, you can still raise your hand. So just so you don't change your mind as you start hearing the answers. So you can raise your left hand, or your right hand, or leave both hands down. There is going to be 3 choices. Either one variant wins, or the other variant wins, or there is no difference. And if you get the result wrong, you can sit down. And at the end, I'm going to ask you, you can type into the chat, those of you who are still standing. We'll see how many people we have who guessed all 3 results correctly. And just to give you some baseline here, that if all of us just guess at random, then about 4% of people will get all 3 questions right. Had 117 participants there, so we'll have, let's say, about 5 people. So our goal is to be much better than random. All right, then let's go. Here is the first example. This is a sales email from Outreach. And you don't really need to read through both versions of the email. I can summarize the differences for you. What we see on the left is more of a kind of a typical sales email. It's a little bit aggressive, and it's very kind of precise, concise, and to the point. And on the right, it's a different version, which is kind of more socially mindful. For example, it says, I'm sure in your role you get a ton of self-driven emails, probably most of which is spam. My goal is to provide enough value to warrant a 15-minute call. So it really tries to be very polite, but contains basically the same information. So the differences are more kind of aggressive versus more polite, but the aggressive version is more to the point and it's shorter, while the polite one is sort of longer. Our success metric is going to be reply rate. Which one of these versions got higher reply rate? So you can raise your left hand if you think the left version, the more salesy one, has a higher reply rate. You can raise your right hand if you think the more socially mindful one has a higher reply rate. And don't raise your hand if you think they are about the same. It doesn't make a difference. It's really all just about content. All right. Let's see. People are typing in the chat. Okay, yeah, you don't necessarily need to type like what you're doing now. Now you just kind of do it by yourself. But at the end, if you got all three right, certainly type that you did it. Okay, I assume you all voted. So let's see. If you did not raise your hand, you can sit down. There was actually a difference. So the framing matters. If you raised your right hand, you can sit down. So the result here is that the left version, the more salesy version, gets a higher reply rate, and not just a little bit higher, a 70% higher reply rate. Now, the caveat here, however, an interesting caveat, is that when we looked at the replies that these two different versions produced, we found that most of the replies for the left version, the salesy one, were actually negative or even unsubscribe requests. So if you only counted positive replies, the right version actually had more positive replies. But by our standard, by our success metric of reply rate, the left version wins. All right, here is a second example. This is a search engine result page in Bing. And the success metric for this experiment is going to be click-through rate. So just on this first page of results. So how many page views got at least one click? And the difference between the variants in this experiment is that version A will show 10 results, and version B is going to show 8 results. So what you see on the right is the version B with 8 results. So the last 2 results would just be that were shown in version A, they will just be moved to the next page, to the top of next page. And everything else just remains the same. So it's only 8 results versus 10, and which version has higher click-through rate. Now you may be wondering why even try this kind of experiment. Sounds like it's pretty obvious. You remove things, you'll get fewer clicks. Well, here is some of the hypotheses and some reasoning. First, if you remove some components from the page, you get a faster page load time. And we know from other experiments that page load time actually has quite substantial impact on user engagement. And then the second argument here is kind of more psychological. Like you may have heard about the tyranny of choice problem, that if you have a lot of choices, you may just end up not choosing anything. Well, if you have fewer choices, you actually are more likely to choose at least something. So those are potential hypotheses here. All right, so now you can raise your left hand if you think the version A with 10 results had higher click-through rate, And raise your right hand if you think version B with 8 results had higher click-through rate. And don't raise your hand if you think they are about the same. I'll just give you a couple of seconds to vote. All right, so let's see. If you raise your left hand, you can sit down. If you raise your right hand, you can sit down. Actually, there was no difference. And it may seem surprising at first. However, this is something that we've observed again and again in our experiments. And in fact, we call it a rule of thumb. That shifting clicks around on a page is easy, but actually producing real improvement, reducing abandonment is actually quite hard. So what happens as you make changes is that users just shift their engagement from one element to another, but not actually substantially improve. Yeah, so shifting clicks is easy, removing abandonment is, reducing abandonment is hard. All right, so now we come to our last example. I hope we still have a lot of people standing. This is, yes, and for those of you who are on Windows machines, please do not look in your left bottom corner, because you'll probably see the answer there. So this experiment concerns the text in the search box on the Windows machines. And what it does is that if you type a query there, it's going to search both on your machine as well as on the web. So the question here is what text to put in order to produce more searches, to incentivize users to search more. Yeah, and the reason why searching more is interesting is because when the query actually goes to the web and users go to the web, they go to Bing, and Bing is going to show them some ads, and sometimes they're going to click on those ads, and Bing is going to make money when they do it. All right, so raise your left hand if you think the left version, search the web in Windows, produces more clicks, more searches. And raise your right hand if you think type here to search produces more searches. And do not raise your hand if you think they are about the same. All right, let's look at the results. If you did not raise your hand, you can sit down. There was a difference. And if you raised your left hand, you can sit down. The winner is type here to search. Now, what's interesting about this experiment is that it actually tested 4 different variants. I only showed you 2, but there were 4. And type here to search was the winner. Search the web and Windows was the worst. So I really gave you a very easy example to guess. But what was also interesting about it is that the number 3 out of those variants was Ask Me Anything, which was the control. And this is the text that which was put there in the initial release of Windows. And this is something that designers decided on based on the user studies that they conducted and all of the thinking, and they ended up in the 3rd place here. So this is again showing that you should stop guessing and just get the data. All right, so now those of you who guessed all 3 examples correctly, type something in chat, and then I think towards the end I'll take a look and see how much more better than random we did. All right, so now let me turn to discussing A/B testing for our machine learning models. Like, why should we A/B test our machine learning models. We have very good metrics, we have evaluation, criteria. Now, those examples that we looked at were mostly about UI and kind of fairly obvious changes. Is there a need to A/B test our machine learning models? So my answer to that would be certainly yes. We should A/B test our machine learning models. And here are my top 7 reasons for why we should do that. The number 1 reason is that training and test sets get old pretty quickly. And I think a lot of companies now can actually observe this in the COVID. During the COVID, it's such a vivid example. At least in the sales space, the whole sales communication just changed completely when the lockdown period started and people went home. When we looked at our machine learning models, a lot of the at outreach, a lot of the things started to immediately getting classified. A lot of the emails start to getting classified into the other category. So things just changed dramatically. So just like this, if you use your static training set to train your model, then by the time you ship it into the real world may have changed. And if you don't actually validate that it works in an online setting, you may not get good results. Number 2 is that training and test set may miss an entire class of examples. A good example when this happens is, again, in Bing. It's very hard to produce a training set which really covers all different kinds of search queries. And maybe somehow, for example, you've forgotten to include, say, weather queries. And then what happened is that you trained a great model, but a great ranking model, but it's going to perform really badly on this set of queries which you did not include, which was not included in the training set. And you can only learn about it, again, if you do an online evaluation with real users and not just an offline model evaluation. The third reason is that labels produced by human annotators may be inaccurate. In the supervised learning algorithms, we need label data. That label data often produced by annotators, but annotators are not real users. And again, a good example that I remember from the time when I worked in Bing, whenever we did such kind of evaluation, annotators tended to always prefer richer kind of richer web page designs with more images and more videos on them. They thought that they were great, and they would always market kind of higher than the plain basic designs. But whenever we tested them on real users, we found that, well, all of this images and videos actually just prevent people from getting to their results fast. In real world, people are in a hurry. They just want to get to that result they want to find. They don't care about all this multimedia. In fact, it slows them down. Another example is that all errors are not equal. So this is typical when we train our machine learning models. We consider all errors equal, or perhaps we have some very basic weighting about it. But in reality, the real users actually may care about some errors a lot more than about other errors. And there is really pretty much no way to mimic that sort of real user preference for different type of weighting for different type of errors in an offline setting. You really need to go online in order to find out what people care about. The number 5 reason is that UI matters. In our offline evaluation of machine learning algorithms, we generally focus on the quality of the model. But how the results of that model are presented to the users also matters a lot. And that factor needs to be tested. For example, if the model has problems in a certain area, there is a certain type of mistakes that we know the model is making, we can actually mitigate some of those problems via UI, where we can provide users other alternatives or create a different experience for users when the confidence in the result that the model produces is low. And that may actually help alleviate some of the issues, making those errors less important. The number 6 reason is that a machine learning model in the modern systems, there are many machine learning models which are sort of all piped together to produce a certain result, a certain user experience. So the model is part of a bigger system. And even though the specific model that maybe you're working on may have improved, it's not at all clear that the whole system is going to improve. In fact, the whole system may degrade because the downstream model which consumes the results of your model may have already learned what kind of mistakes your model tends to make and learn how to correct for it. And when you update your model, change the distribution of errors, that may lead to degraded performance of a downstream model and not an improvement. And then finally, perhaps the most common reason is that model implementation may have a bug. You may have created the model, you've tested it, it works great, but somehow, as it was being deployed into production, something happened either to the model or to the data that's being passed into the model. And there is a bug, and model actually does not work as well as it was originally in the development environment. So all of these reasons essentially say that we cannot just trust our offline evaluation of machine learning models. We need to do an online evaluation via an A/B test. And the way I view it is that there is that virtuous cycle here, that we have our machine learning model, and we can use A/B testing to measure the end user impact of this model. And in return, what we get is we can obtain learnings and insights, for example, into all of these 7 areas, which we cannot actually get in an offline way, which we can then use to improve our model. All right, so hopefully with that, I've convinced you that it makes sense to A/B test machine learning models. And what I'm going to talk about now is what are some of the lessons and pitfalls, some of the gotchas that if you go and try to actually do it, that you should be aware of. And I'll go through them one by one. Oh yeah, so before I go into the pitfalls, I'm going to use some examples from outreach to illustrate some of the pitfalls. And for that, let me just briefly describe for you what outreach is. You can understand those examples. So outreach is a product that sales reps use. So it's a platform for sales reps. They use it on a daily basis. They work in outreach and do all of their activities in outreach. And it enables them to be more effective and more efficient. And what we use AI for in outreach is first optimizing the sales process. So you can look across all the sales reps in the company and understand how good is overall the process that they are following and maybe help improve it. As well as we use it to personalize customer interaction. So help sales reps provide some suggestions and advice to sales reps in different situations about what they should do, how they should respond, and what kind of content they could use to to better communicate with a specific prospect or customer. All right, so let's look at the lessons. So this is the first lesson. AI versus no AI tests are actually tricky. So the scenario here is that you have a product, you have a system or a product area which currently does not use machine learning, but you want to introduce a machine learning model into it, and you want to measure the benefit of introducing that machine learning model. An example scenario here that kind of running example I'm going to use throughout is that we want to build a machine learning model which is going to recommend to a sales rep the best content to respond to a prospect's email. Right? So the sales rep is going to approach the prospect replies back, and they say something, and most of the time it's some kind of an objection, some reason why they do not want to buy your product. So we want to help sales rep by telling them, suggesting them how to respond. Now, what the problem here is that when you introduce a machine learning model into an existing system, it actually requires quite a few changes to the architecture. You probably need to build many backend components. There is a new service that is being deployed. And all of those components may actually impact the outcome of the test. So it's not only the suggestion itself that we are producing that impacts the outcome of the test, it's all of those backend components may actually slow down the system or have some side effects, which may also impact the outcome. So the problem here is how do we kind of disentangle the different types of effects? So the solution that I recommend is to run this experiment when you're running an A/B test to evaluate your machine learning model, not just run an A/B test, but run an A/B/C test with the following variants. The variant A is going to be the control. This is just normal product. There is no machine learning at all. The variant B is what I call a hidden AI. What we are going to do in the variant B is we will run our machine learning model in the background, but we are not going to change the user experience. So all of the backend would execute, but we'll just not use the results. And then the variant C would be the full AI, which is we run the machine learning model and also make a change to the user experience. Now, what this design allows us to do is that we can exactly measure these two different components separately. When we compare A to B, that gives us just the impact of all of those backend changes. Most of the time, it's performance-related type of impact. So we'll know what impact that has. When we compare B versus C, it's only the impact of new user experience, because both B and C have the same backend components running. The difference is only the user experience. So we'll know the impact of the user experience part. And then when we compare A versus C, we have the aggregate impact of both, which we can use to make the ship no ship decision. All right, so this is the first lesson. Now, second lesson is to ensure equal learning opportunity. Now, the scenario here is that for models that learn and adapt on the fly or get retrained very, very frequently, the quality of that model depends to a large extent on the amount of data that goes into that retraining process. For example, we may be retraining our rep content recommendation model on a daily basis based on user feedback. And when we recommend to sales rep a piece of content to respond with, they can either accept or reject. Whenever they do it, this becomes a labeled example that we can feed back into the training, and every day we retrain the model. Now, the problem here is that if the two variants A and B in our experiment have different number of users, then the model which has larger fraction of users will actually get more feedback, more training data, which is unfair, may lead to a bias. That model may appear to be better, but actually it's better not because the model is better, it's better because it gets more data. So the solution here is pretty simple. We need to ensure that the treatment and control are exposed to the same fraction of users. We can't really run unequal experiment. And another kind of caveat is that if we are not running a 50-50 test, that we are not using all the users, which means we have our A variant, maybe 10% of users, B variant, another 10%, and then there is an 80% of kind of a default, all the users who are not in the experiment. Now, what we need to make sure is that when we retrain our control model, that we are not using the data from those 80% of users who are not in the experiment, because that, again, will be very unfair to the treatment. I've actually seen that happen. So that's the second lesson. The lesson number 3 is to be able to zero in on the target scenario. So what often happens is that our machine learning model may target an improvement to kind of a very specific narrow user scenario. So in our example of recommending a sales rep some content to respond, we may decide that we only build a model for a specific type of objection, for example, a cost objection. Whenever a prospect replies that, your solution is too expensive or we don't have budget, essentially the money-related objection, we are going to show something, but it's not going to be applicable to any other responses. Now, the problem here is that only a subset of deals may face a cost objection. So if we just analyze the results of our experiment across all deals, then we have a lot of noise, a lot of the deals which are essentially irrelevant. And whatever signal we have from that maybe our model is generating may just be drowned in that noise, lost in that noise. So how to deal with this? One solution is triggering, which means restricting the experiment analysis to only the affected population, the affected set of deals. Now, this sounds very simple, but in reality, this may actually be fairly tricky to implement. It's very easy to see in the treatment what are the deals which were affected, because those are the deals where our model fired. Right? So those are our deals. But in the control, there is no model, so it's not firing for anything. So how do we know what are the right set of deals? And often, in order to create that sort of equivalent population in control to compare to, we need to do what we call a counterfactual logging, which, for example, may take the form of running the model in the background in the control as well, but just not using the results. So again, that sort of a design of an ABC type that I mentioned before is also useful here. Because we want to run the model, we want to log that we've run it, and then we use that log to extract the correct population for the control. All right, lesson number 4 is to beware of side effects. The scenario here is that we may, for example, be improving our model to make it better for a specific scenario, such as cost objection, but we may inadvertently, negatively, or maybe positively impact other scenarios as well. because a lot of the time it's a single model. We may have enhanced, for example, the training set with a training data for a specific scenario. And we think that other scenarios are just going to be fine, but actually that may not be the case. So the question is, how can we detect those issues? So the solution here is kind of the opposite from the previous one. If we run such an experiment, we should do triggering in order to understand the impact of our model on the scenario that we are interested in. But also at the same time, we want to do an all-up analysis as well, because that's where the side effects would show up. And some other ideas that can help is to use a large comprehensive set of metrics. So not only limit the metrics to the specific scenario you're interested in, but have also all other metrics that potentially could be affected, included in the evaluation. And another thing that you can do is to use segments. For example, segment the population by various categories that make sense in your experiment. In our scenario of sales, useful segments can be objection scenario. You may actually have a separate analysis for every objection scenario. Or persona, which is what is a job title, essentially, the persona of a prospect that the sales rep is reaching out to, or industry, that perhaps our model works better or worse in a certain industry and for a certain persona. Yeah, so when you do that, it is very useful to do that, but there is one caveat, is that as you start segmenting your population, you start doing more and more comparisons, and that leads to the pitfall called multiple testing. Essentially, your probability of seeing a statistically significant result just by chance increases as well, the probability remains the same, but the chance that you see a statistically significant result just by chance goes up. So in order to do that, you need to be careful, and there are different ways to deal with this multiple testing problem. And one of the simplest ways would be just to use higher thresholds when you are determining the statistical significance. Or lower thresholds if you are using a p-value, but more stringent criteria. All right, and the lesson number 5 is to measure the full machine learning pipeline. And the scenario here is that often the output of the final output, the user-facing feature based on machine learning algorithm, actually the results of multiple machine learning models kind of stringed or piped together. For example, our rep content recommendation model may consist of 3 different models. There may be a named entity recognition model, which would detect known entities, for example, competitors mentioned in the email. There is also a scenario detection model, which is going to tell us what kind of objection the sales rep is facing. Is it a budget objection? Is it a bad timing? Or what kind of objection it is? And then finally, there is also a recommendation model, which, given sort of all of the above, some of the interesting entities that were detected, and given the scenario that was presented, would determine what is the best email template to respond with. And if we want to maximize the learning from our experiment, we really want to understand how each one of these parts actually impacts the end result, how the quality of each of the models impacts the end result. Now, in order to do that, the first thing that you need to do is to log the result of each of the model, not just the final thing, as well as its confidence level. And after that, what we can do is we can create segments based on the confidence as well as based on the prediction class. And then we can use that segmentation to understand for different levels, for example, for different levels of confidence of scenario detection, how well our recommendation performs. Now, the caveat here is that our assessment of confidence need to remain the same in both variants, because if we change how the confidence is computed, then we essentially, and then we segment our results by confidence scores, then we get incomparable populations there, and the results will be invalid. All right, so this is all that I wanted to say. So what are the takeaways here? If you remember just one thing from this talk, I say let it be this first bullet point here, that we are, as humans, very bad at assessing the value of our ideas. So don't trust the experts, don't trust yourself, just get the data. And A/B testing is the best scientific way to use the data to measure the causal impact of your idea on users and business. And hopefully I've also shown you that A/B testing is not just for UI. And A/B testing and machine learning models will actually help you gain deeper insight and perhaps save you from some embarrassment when you ship the results to production and your great model to production and it doesn't actually work. And when you embark on applying A/B testing to AI, these are the 5 things to keep in mind. All right, so this is all, and now I'll be happy to answer any questions. And I'm also looking forward to check how many people did we have who actually got all 3 results correct. Now looks like we got 2, 3 maybe. Well, there must be more than 3. All right, yes, I see. So you can, I guess you can type the questions in chat. I don't know if you can unmute yourself and ask either way. I'll just answer from chat right now. So the first question there, for the example number 3, why did that left variant win? What was the logic and the reason over the one that was on the right? You know, that's actually a very good question, because A/B testing by itself does not actually just give you an answer to why. It does tell you which variant wins, but it doesn't really explain you what is the theory kind of behind that. However, often A/B testing can help you understand and kind of devise a theory. And the way to do that is to introduce kind of more diagnostic metrics into the test. You can have a success rate metrics. For example, in there, it was the number of searches. So if that's the only metric you have in an A/B test, all that you will know is that one variant has higher number of searches than the other variant. However, if you also try to capture, for example, the categories of the queries, and you'll understand the distribution of the different types of queries that were happening in one variant versus the other, then it will tell you what kind of queries, what kind of searches are happening at a higher frequency and what kind of searches are happening at a low frequency. And that will maybe give you some idea of what may be happening there. And similarly, you can also introduce other types of metrics that will kind of not explain, but will potentially point you in the right direction on where to find an explanation for the result. All right, so that was that question. Let's see, what are your preferred statistical tests? Yeah, so the most common statistical tests which to my knowledge are used in A/B testing is a t-test, which is used to compare the means, the averages of a certain metric for the two groups. And then the chi-square test, which is used to compare the proportions. So chi-square test is used for diagnostics. For example, you do want to make sure if you run a 50-50 experiment that you have roughly equal number of users in both variants. And it's not going to be exactly the same because there is some randomness. But you want to know that there is no statistically significant difference. So chi-square test will generally be used for something like that. So there are also a lot of different tests exist. And there is certainly evidence that for certain types of data and for certain types of metrics, different tests give a slightly better result. My personal opinion is that simplicity is maybe worth more than the kind of the sophistication and the slight gains in the power of the test that can be obtained with more complicated, more sophisticated tests. So I generally just prefer to keep it very simple. T-test and chi-square test is what I normally use. All right, another next question. Could you explain how you do significance testing when B and A are 10%? When the B and A are, for example, 10% and 80%. So it's all done in exactly the same way. Like if you look at the formula for t-test on Wikipedia, there is nothing that requires you to have equal number of like users or data points in each group. However, it does have impact on power. And in order to obtain maximum power, you actually want your groups to be equal. So generally speaking, the rule of thumb is you should always have the equal number of users in the treatment and control. And unless there is like a very specific scenario and very specific use case where you don't want to, or you cannot do it for some reason. All right, let's see more questions. How do we handle multiple A/B tests for a big application having several features ready for productions? What precautions we need to take while designing these experiments? All right, yes, also a very good area to discuss. So in general, as kind of A/B testing practices evolve in the product, you will want to run multiple A/B tests on different areas. For example, Bing was running hundreds, maybe even thousands of A/B tests concurrently at any given point. So running A/B tests concurrently, running many A/B tests concurrently is not a problem. In fact, it's desired because you do want to evaluate ideally all of your ideas, all of your decisions, and you don't want to hurt your agility. You don't want to wait for one test to finish before you run another one. However, the problem that may arise is what we call interaction of this at the same time. That obviously is not going to be fine. So that's what we call an interaction, when the result from a combination of experiments are not actually equal to the sum of the results of individual experiments. And that may happen even though, from what I've observed, in practice, it's much more rare than sort of you may think of it in theory. But you still, especially if you are running many tests, like hundreds of thousands, you certainly need to take care of interactions. And the true approach is to prevent interactions. And the way you can prevent interactions is to run experiments on non-overlapping sets of users. For example, you have two experiments. You suspect that they might be interacting. Now, then, in order to avoid that, what you can do is you dedicate 50% of your users to experiment 1 and the other 50% to experiment 2. So they are running on non-overlapping populations. There's one approach which works for known interactions. And then you would also want to run a certain process in the background to detect some unknown interactions. Perhaps experiments just happened without people being aware and they are interacting. And there are ways to detect those interactions. It's also a statistical test that you can run. If you have two experiments, you can test whether they're interacting or not. So it is important to take care of the interactions. All right, next question. Do you have any suggestion to do A/B testing on job application as a job seeker to find out which resumes will get interviews? So let me see if I understand this. A/B testing. Okay, so I see. So the scenario is I'm a job seeker and I can prepare different kinds of resumes and I want to A/B test which one of my resumes works best. Yeah, well, this is possible. The only thing is you need sort of I don't know if you'll get a large enough sample size. But if there is a big difference in quality between your resumes, then even without a large sample size, you may actually be able to obtain a result. In fact, I don't know if that's ethical, maybe, maybe not, but what you could potentially do is you don't actually put your real name on that resume, you kind of anonymize it, and you send both versions of the resume, you can send to the same company, because that will allow you to do a paired t-test, not just a normal t-test, but a paired t-test. And that's actually much more sensitive, because you'll have the data points on both resumes from the same company. So that's much more sensitive. But yeah, that is possible if you have a large pool of companies to apply to. All right, another question. For experiment 1, to test the hypothesis targeting positive-negative response, how would you set up the test and control groups? Okay, so yeah, so this is an example of outreach. So there is, I think, maybe two aspects to this question. One aspect is the success metric, as I think you've all noticed from that example, and the reply rate is not actually a good metric to evaluate your quality of your emails, which is very interesting, because we all use emails. Emails also by far the most popular approach, most popular channel for salespeople. But there is actually no just naturally good metric which will tell us how good the email is. All we get is a click rate and open rate and reply rate, and none of them is actually a good metric. So one aspect there is that we do need to figure out a good metric. For example, positive response rate will be a much better metric. But in order to determine that the email is positive, we actually either need people to manually, label it, or we can train a machine learning model. So this is one way of how AI and machine learning can improve A/B testing, is we can use AI and machine learning to come up with better metrics, more sensitive and more correct, more metrics which are more aligned to our business goals. So that's one aspect of it. We need that metric. And then in terms of how to set up the test, that is actually fairly simple in a platform in a platform like Outreach, because what Outreach does, it automates a lot of sales tasks. So if a sales rep is trying to reach out to a certain prospect, they have what we call a sequence, which is just a set of activities that they want to do. And that's usually prescribed actually by the manager. For example, a sequence may start with an email, then be followed by a phone call, and then another email, and then a LinkedIn message, and then another call, and another email. And each one of those emails will have a template. And some of those emails may, like the templates that I have shown you, actually a completely automated template. There is nothing for the sales rep to edit. We just send it automatically. So whenever the time comes to send that email, we are going to do our randomization, and we are going to decide which of those emails, which version of the email we are going to send to that prospect. So the randomization there is going to be at the prospect level. And we at Outreach, we actually have a way for our customers to run this kind of A/B tests in an easy way. All right, next question. I really like that you guys have a lot of very nice questions. Really hitting some of the very good points with them. All right, train test sets get old. If data distribution in the training set changes quickly enough, we cannot capture by training window, then even if in A/B test, we think model A is better than model B, how do we know that's still the case after the A/B test? Yeah, that's a very good point. So I think the key point there that when the data changes very quickly, then the result of our A/B tests may not last. And again, a great example, actually, the COVID scenario. We may have two versions of the model, and before COVID started, one version behaved better than the other. Actually, after COVID, they may very well reverse. So one way to and there is like generally, of course, as the world changes, we just need to keep up with the world. And that's the best case. We just need to train our models quickly, and then we evaluate them for slightly different time periods, and try to find out how quickly the quality degrades of the model. That's outside of an A/B test. You could just run some experiments and figure out how quickly the quality degrades with the world changing. That will sort of give us an idea of a time window in which the model is still valid. But then what you can do is you can use A/B testing to sort of evaluate not just the model itself, but your essentially model training process. For example, you could ask, what's the difference between updating the model every day versus updating the model every week? So you can actually have those two pipelines, one updating the model every day, the other one updating it every week. And your two groups of users are going to get those two different results. And that will sort of help you inform how quickly you need to update your model, which is potentially the cost-benefit trade-off. It may be very costly to train new models, a lot of compute power. And then you can find sort of an optimal balance there. All right, hopefully that answers it. And another question, train test set misses examples. If we ran A/B test on sample traffic, don't we still have the same problem? You do want to run A/B test on a large enough traffic, or you need to run it on a small percentage, but longer. So generally a good approach to execute an A/B test is that you start small. For example, you just start your A/B test on 1% versus 1% of population, and you run it for a few days. And the goal of that initial period is to really see that there is no like a terrible bug in that A/B test. Because if there is a bug, you will see it even on a small percentage, because it's going to be a huge difference in metrics. You will not need to have many samples to detect it. Like I remember in Bing, we had a system which would detect big degradations in just a matter of seconds. So after a few seconds of starting a test, it would detect automatically a degradation and would shut the test down also automatically if something bad is happening. But then after this initial period, you can really start ramping it up. You can go from 1% versus 1% to 10% versus 10%, and then maybe to 50% versus 50%. Because you do want to get that comprehensive evaluation to kind of avoid this problem. If you keep just 1% versus 1%, it is true that you may miss some of those cases. Even if you don't miss those cases, corner cases, they may be so rare that they're not actually having a substantial impact on the result. And if you segment, say, by different type of objections or by different industries, there may just not be enough data to see a statistically significant differences in those segments. So it's certainly recommended that you ramp up your test to a good large sample, ideally 50-50. That's kind of my rule of thumb. You can start small, but every test end it at 50-50. All right, next question. What tools do you use for running and deploying an A/B test? There are a lot of A/B testing vendors, because right now A/B testing is essentially, in software development, it's essentially gold standard. Pretty much every software company would use A/B testing to, at least every B2C company. I would say B2B, it's a little bit delayed, the progress there. But every B2C company would use A/B testing. So there are many tools, many vendors, which provide A/B testing capability in a fairly easy way. Essentially, they give you a library. You embed that library in your product, and they give you an UI that you can use to configure and set up your tests. And once you start it, that library is gonna ping that system. It's gonna have all those test configurations. Your code is going to ping that library. And it's actually very easy. In fact, you can set it up and try it in a matter of a few hours, like certainly in a matter of one day. You can try it out. So some vendors are Split, LaunchDarkly, Optimizely, and there are probably others. Those three are maybe the more well-known ones. Yeah, and then for big companies, they all tend to eventually build their own A/B testing platforms. Like Microsoft has an internal A/B testing platform, which is kind of tailored to Microsoft, integrated with their software development and release practices, so that, for example, when you release a new code to production, and it goes through a set of rings of different kind of pre-release populations. A/B tests just kind of automatically get run in those populations and so on. So the big companies tend to build their own, but for everyone else, vendors are kind of abound and easy to use. All right, another question. If the power is a problem when groups are not equal, is there a way to downsample the large group to fix that problem while avoiding breaking the statistics? Oh, yeah, I think maybe I didn't quite explain it clearly enough. The power is not a problem. So if you have 10% versus 10% A/B test, and you just decide to add another 10% to one of the groups, your power actually is going to go up, not down from that. However, if instead of doing this, you actually run a 15% versus 15% test, then your power is even higher. Yeah, so it's not about breaking the statistics. It's about the most efficient use of traffic. If you already allocated 30% of users to this experiment, the most efficient way to use it is to split it equally. But if you don't split it equally, it's not going to break anything. Another question, what machine learning model do you run to perform A/B testing? So A/B testing itself does not have a machine learning model built in. It's actually a very simple process that I just described on that slide. You need a randomization module, which is going to randomize your users into one variant or the other one. And then when you compute the results, collect the data and compute the results, you need to run a fairly standard statistical test. So at least in theory, it's actually very simple. Now, however, in practice, there are a lot of caveats. So even to implement this simple process correctly is not easy. That's why I normally recommend people to actually use a vendor rather than decide that you want to build your own A/B testing platform in your company. At least certainly, not unless your A/B testing sort of grows to a large scale. You start running like hundreds or maybe thousands of A/B tests concurrently in multiple groups on multiple products. Then probably it's both kind of cost-wise, but also customization-wise, it's worth building your own A/B testing platform. But before that, it's probably not worth it. All right, I think those are all the questions. So I was looking, I guess, let me see. Those are all the questions in chat. I see there is a separate Q&A box, which is separate from chat. However, I don't seem to be able to open that.
Oh, you should be able to open the Q&A box by just hitting the Q&A button. It's right next to the share screen button.
Yeah, I'm trying to, but somehow it doesn't open for me. Let me see if I stop projecting, and then maybe it will open. I'll stop sharing. Okay, yeah, so now that I stopped sharing, I can see it. All right, great. I set another set of questions here in the Q&A box. So we can go through. What are some of the pitfalls of A/B testing? That's actually a very good question. Someone asked right before the talk is even started, which is very nice. So I think the biggest pitfall, the biggest problem with A/B testing is when your test does not execute correctly. Because A/B testing is very sensitive to everything being done correctly. Like your randomization of users in the variance actually really need to be random. If there is, even in a corner case, some kind of a bias there, then the result of the whole experiment can be invalid. So that's maybe the biggest pitfall. Another pitfall is when you're trying to interpret the results. It's having the right metrics and then interpreting those metrics correctly. And there the problems may happen, especially if you run a lot of A/B tests. And there are a lot of people who are running experiments who may not even be familiar, even at the level of this talk, with how A/B testing actually works. They're just looking at results and trying to make some decisions, and they may make mistakes. There is actually, I can recommend you a paper that me and my colleagues have written. It's called A Dirty Dozen, 12 Metric Interpretation Pitfalls. So you can read that paper, and it talks about 12 different ways how you can actually misinterpret results from even a valid A/B test. I would say maybe those two are the main ones. All right, another one. Is it possible that moving the first sentence of an ad into the title just increases by 12% the chance that a user accidentally clicks on the ad? Yeah, so again, I think the explanation on why is difficult there. However, I think in that example, in the very first example that I shared, there is some evidence that this is not the case, because Bing has a very comprehensive set of metrics on the quality of user experience. And it does include things like if you click somewhere accidentally and you go back immediately, like that will be captured as a negative signal that you've clicked on an irrelevant result. And so that did not degrade in this case. So probably that is not the case. All right, another question. Question why A/B testing mode. Okay, I think it's the same. I think the same question that I answered in the chat. Okay, another question. If you are a startup, where can you find a sample database of customers to do A/B testing? Yeah, so if you are a startup and you really have a small number of users, you can still do A/B testing. But what you will care about in that scenario, which is actually anyway is going to be true because you're a startup, you will not really care about 1% change in some metric of interest. You're looking more for kind of breakthrough ideas. You're looking for things which are going to change your conversion rate by like 50% rather than by 1%. Because you're not yet big enough to care about all this. You're going to run out of money if you try to essentially get there by making like 1% change and then another 1% change. You need big ideas. And the nice thing about statistical testing is that your ability to detect statistically significant changes actually depends on the size of the effect. And the bigger is the size, the easier it is to detect it. So if you care about 50% change in your metric of interest, you only need a couple hundred users actually to be able to detect it in an experiment. What types of algorithms are used for A/B testing? I think I answered that. Okay, when you have an ABC in a test, you mentioned test A versus B and B versus C. My question is ABC test in the same time better to use ANOVA, which is another method? Yeah, so there are different, there are different methods that you can use. I'm personally always sort of prefer the simplicity, maybe because especially now, even at Microsoft, I think I did, but especially now I train by salespeople. You know, the users, the people who are actually running A/B tests at Outreach, they're salespeople. They are not engineers, not data scientists, not product managers. And things has to be really, really simple for them. So I generally prefer that you just, as far as you can, not introduce to a lot of different methodologies, but it is certainly possible to use something like ANOVA. I answered that. Okay, the last question there. Do we look at the distribution of errors or data to determine the applicability of the trained model? Distribution of error or data. So when you, yeah, that's an interesting question. So certainly when you run an offline evaluation of your machine learning model, you always want to do error analysis and to understand what kind of errors the model is making and how to improve the model based on that. In an A/B test, which is you're testing already the end user features, not just the model, in kind of a general case, you may not always have ability to know whether the model is made an error or not. However, in some cases, you might have it. And the cases where you may have it is where you have a feedback loop. For example, if you have a recommendation of how to respond to a prospect's email, and user accepts or rejects the recommendation, then you may know on in what kind of scenarios for example, more rejections have happened. So in that sense, you will want to create some metrics based on it, which would measure, let us say, a fraction of suggestions rejected in specific scenarios. And that will you create one metric for each scenario like that, and that will give you a sense of a distribution of errors. And that may be very helpful for understanding where the model is not working. All right. Let's see. Well, now there is another question, maybe the last one in the chat. What percentage of B2B sales forces actually use A/B testing or ML for their sales calls? Yeah, well, in the sales industry, A/B testing is still not a common practice. So I think it is a work in progress. At Outreach, we provide A/B testing functionality, and we'll look at how many customers. We have around 4,000 customers, a little more than 4,000 customers. What fraction of customers actually use A/B testing? And I'm not sure I probably cannot tell you the exact numbers there, but it's certainly not all customers. However, what we see is that at least the larger customers, the enterprise and sort of corporate segments, they're very, very interested in A/B testing and in how they can use it for sales. So when we talk with those customers, they always ask about it. And that's kind of one of the top of their mind is how they can become more data-driven, how they can improve the sales process. And the reason is that right now, for the most part, the way sales process is defined, it's not a very data-driven way. It's the sales VP, some marketing people, sales operations, they just come together and sit and decide, like, here is what we are gonna do. And that's pretty much that's pretty much how the process is defined. And people are starting to understand that often however, the way they defined it is not very good. And certainly there is always room for improvement. But how to improve it is not very clear. So A/B testing is that way, one way for them to actually, in a systematic way, to keep improving their sales process over time. And I think in bigger companies, they realize that. In smaller companies, maybe not so much yet. All right, I think that's it. Thanks, everyone. Those were great questions, and a lot of them. You're, I think, one of the more active audiences. I gave this talk quite a few times before in different venues. So that's great to have such an engaged audience.
Thank you. I think there were actually two more in the chat again, if you go ahead and look there again.
Oh, all right, great. I'm happy to answer more questions. Oh, yeah, that's right. More questions, yes. T-test has the significance level. So if you run 100 tests with very similar changes, it may accept, reject some of them for the wrong reason. How you will deal with that? So I think this relates to the fact that there is a possibility of a false positive. You know, if you run a test where A and B are the same, exactly the same, then 5%, your distribution of the p-value, which is the value that you use to determine the statistical significance, is actually uniform, which means if you run a test which compares exactly the same things, no difference at all, 5% of the time, you will actually see a statistically significant difference. So I think that that question alludes to that, of how do you deal with this? Yeah, and this is the same problem which also I briefly mentioned, that if you introduce a lot of segments, a lot of segmentation of your population, and start looking at the results of each segment, you may just by chance see something statistically significant there. So there are many methods in statistics to deal with it. And the simple one is something called Bonferroni correction. And essentially what it says is that if you perform like n statistical tests, suppose you have like 10 segments, you perform 10 statistical tests, then you need to divide your statistical significance threshold by 10. So if before your significant thresholds maybe was like 0.05, p-value of 0.05, you do 10 tests, now it's 0.005. So this is very aggressive, actually. There are other methods which are less aggressive, but there are this kind of corrections that you would want to apply to the p-value. And another angle to it, another thing that you can do is that, especially over time, as you run more and more tests, you will see that when you see a real results, there is a certain pattern to it, that it's not just in one metric is changing. There are many different metrics which change in a certain pattern, in kind of telling a story that makes sense. It's not just kind of out of the blue random change. So you would also look for those patterns as well, and see that if there is no pattern, it's just somehow one metric has changed, but other metrics which normally also change when this one changes, they didn't change. That's a sign you may be looking at a false positive there. All right. In your experience, do offline metrics correlate much with online A/B testing results? Yeah, this is actually also a very good question. And actually a research problem. There are research papers written on this topic of how do we align our online and offline metrics, because it would be very nice if our metrics that we use offline to train machine learning model would perfectly correlate to the online metric. Now, I think from some of the examples that I shared, you can probably already see that that sort of perfect correlation, perfect prediction there is not possible. Because in an online world, there are just so many more factors other than the quality of the machine learning model that impact the result. So it's never going to be a perfect correlation. But still, you would like to ideally avoid the situation where your offline metric says your model is better, but you test it online and the results are actually worse, which may happen, and I've seen that happen. And how to align those metrics is a difficult problem. There is really no kind of a recipe that I'm aware of. It depends very much on the domain and on the specific model and on the specific user feature that you will be developing based on that model. So within a specific scenario, there are it is usually possible to at least it is possible to run some maybe learning experiments to measure how your offline and online performance correlate, and then try to define better metrics. For example, a better weighting of errors, of different types of training errors, to improve that correlation. So there are methods that you can use to improve it, but it's kind of case by case dependent. All right, another question. Do you want to do an A/B test on which audience is more responsive, virtual or real? This is very interesting. Yeah, I don't think we can do an A/B test, but my experience actually up until today has been that real audiences were much more responsive, because I have done recently even more than one tutorial at some of the conferences, and I was kind of somewhat surprised by lack of participation and response to those tutorials when we do it online. While before, when I used to do some of those talks and tutorials in person, the same talks, same tutorials, similar audience, there was a lot more engagement. However, today, you guys may be proving me wrong, because today you were very active. All right. Great. I think now we covered everything. And if any of you have more questions, feel free to connect with me on LinkedIn and send me the questions. I'm very happy to answer. Also happy to point you to some resources where you can learn more about A/B testing.
Yes, well, thank you all for attending the talk, and thank you, Pavel, for your time. Magnimind really holds these talks with the hopes to inspire people to further their learning. So if you want, please go connect with Pavel and ask him any of your questions to further that. But just by coming here, you've done that today. If you haven't already, please make sure to subscribe to our YouTube channel and comment what you thought about today's meetup or what you thought about our Zoom online format. Also, please make sure to tune in for our next scheduled workshop on July 29th, where we'll be having a data science and workshop called Multi-Billion-Dollar Search Engines. Thank you and have a good night.
All right, thanks everyone.